Hello everybody, today I'd like to talk about a new method we've designed to test macrocycles to see if they will bind a protein surface. The problem is designing a peptide mimetic that will fit on a protein to maybe impede a protein-protein interaction or select that protein, say on a protein surface. Loops are harder to mimic than sheets or helices because they're more diverse. They can be short and fat, they can be tall and thin. They can be wide or curvy, just like people. They're very, very different. So this is a mammoth problem. If we have a loop at a protein-protein interface, for instance, how could we mimic that? In our group, we started working on peptidic macrocycles a long time ago, and this is one of our first compounds, a compound we call D3, which did very well. It's reached at least phase 3 of dry eye disease clinical trials. We started working on that in 1998. Now lots of people work on cyclo-organopeptides. That's what we're calling these now. They're cyclic, they've got an endocyclic organic part and a peptidic part. And of course, in a cyclo-organopeptide, you can vary the organic to maybe change the conformation and the pK properties, the ring size, and of course, you can vary the amino acids that are put into the loop. How do we choose, first of all, the organic fragment? Well, the number one favorite way for most people would be intuition. Just think of what would be cool to put in that place. The other way to do this is with zinc, and we did both actually. We filtered zinc for functional groups that we could use to cyclize, and organic fragments that were rigid. We developed a little MD program to sort those out, and for cost. And after this process, starting with millions of compounds, we arrived at 80-something. Okay, so we've got 80-something different organic fragments that we could use if we're going to do docking with these on a protein, and we vary every single amino acid. Logistically, that's a hard thing to do. That's the problem. If you're going to dock all the combinations of organic fragments, amino acids, and ring sizes, it's going to take a lot of computational energy and probably a lot of time. Our hypothesis is designed to vastly streamline this process. We're supposing that cyclo-organopeptides can be mimicked using only ALA residues. And this doesn't give us the final solution, it gives us the solution for the backbone conformation. And we model those backbone conformations in an aqueous solvent box. We suppose that those are the backbone conformations which are allowed. Using all ALA doesn't allow side-chain to side-chain interactions, and it pretty much ignores solvent interaction, and of course it ignores the protein. We're just asking the question, if you put that number of amino acids and this organic fragment into the mimic, what are the preferred conformations? Say below 4 kilocalories per mole from the minimum energy one that we found. Our intention is to systematically overlay these with the loop on the protein ligand, and when we get a good overlay, that reveals the side chains incorporate into our mimic when we make it. Let's say this is, in green, the target protein ligand loop. That's the interface loop that we want to mimic, and we're going to overlay systematically all the low energy conformations that we find for all the ring sizes using all the organic fragments. But if we find one that overlays well, then it tells us the target backbone to make. And in this slide, I've shown it to be 5 amino acids with that particular organic fragment. We don't make that one. We look at how those 5 amino acids overlay on the protein loop in the crystal structure of the protein-protein interaction. We must have structural information, and that will tell us, make, say, serine, threonine, valine, isoleucine, it looks like, in those particular positions. Let's talk a little bit more in detail about how IBM works. I'm showing a loop that could be an interface loop in a protein-protein interaction. So we came with our library of organic fragments incorporated into cyclo-organic peptides, and we've done molecular simulations, and we've got low energy backbone conformations, and we take each of those and we systematically slide each one around different residues. And some of these things won't fit anywhere. But if luck is on our side, we'll get one that fits really nicely. And when we find a good hit candidate, then we go back and we look at the overlay on the interface loop, and we deduce which amino acids to put in the cyclo-organic peptide when we make it. IBM simulates core conformations of cyclo-organopeptides to find ones which populate those corresponding to interface loops, because what we want to do is mimic or disrupt protein-protein interactions, or simply find a ligand that binds on the surface of a protein. It's based on a hypothesis, and the hypothesis is that the core conformations matching the interface loops can be simulated in solution using all-aller peptide. When we actually find one that overlays well, we make a similar cyclo-organopeptide, except it contains the native side chains corresponding to those which bind the protein receptor at that loop region. This dramatically reduces the number of molecular simulations, because each cyclo-organic peptide made with only alanine represents, say, 18 amino acids at every different position. So there's a lot of combinations of those, which by a conventional docking technique would have to be tested. But we just do those cyclo-organic peptides corresponding to the different ring sizes with the different organic fragment. And in our case, that was about 600. We simulate the core conformations of these virtual libraries once, and we can apply them to any PPI. Once we've done it, we're not using docking data on a particular protein receptor, we're just matching with the crystal structure coordinates to find the best overlay. Chen Xiangmi wrote the computer scripts, did the molecular modeling, made the compounds, and performed the biophysical assays. He's the one on the right. Thank you very much for listening. Goodbye.